Hello everyone, we are continuing with the chapter Gaseous Law and Thermodynamics. In the previous lecture we did some questions based on the formulas and the concepts we have learned till now. In this lecture we will focus more on the PV diagrams, right? The questions which are coming from the diagram basis, because the diagram is sufficient in expressing more or less the whole process, right? And the most important concept in the thermodynamics is these processes only, how the gas is taken from one state to the another. And so we will do some questions based on that and try to learn some new techniques to solve the questions. Okay, so let's begin. So the question says that you have this PV diagram given to you. The gas is in a state A. It is taken to two states from A. One is B and one is C. Right. The pressure value, volume value, over here is 16. Over here the value of volume is 1. And at B it's 4. Right. So basically the figure shows a process of an ideal gas, right? Temperature at A is given to us as 600 Kelvin. Pressure is given to be 16 atm. Okay, and the volume is given to be 1 liter. So this is the state at A point, right? Volume at B is given to us 4 liters. Out of the two processes, that is AB and AC, right? One is adiabatic and one is isothermal. Okay. From AB and AC, one is isothermal and other adiabatic. Okay. Now the ratio of the specific heats of the gas, that is gamma, is equal to 1.5. It is a special type of gas given with gamma 1.5. Okay. So what all you need to find is, first, which is the adiabatic process. Okay. So this I don't think would be tough, because as we learned the property that starting from a same point, if there are two processes, the slope of the adiabatic process is more. So that is, this process has a slope more than the above process. So we can say that AB is the adiabatic process, because the pressure is falling very quickly in this, right? Now let's try to answer the second part, which says that compute the pressure PV and PC. Now we know that this process is adiabatic. As I told you, the first thing you have to do is identify which type of processes are these. Adiabatic expansion process. This is isothermal expansion, and this is obviously isobaric expansion, right? So all three processes are expansion processes. One is the isothermal, one is adiabatic, and one is isobaric. Now you have to find the pressure at B. So obviously it is governed by the constraint equation for adiabatic process, which is nothing but P1 V1 raised to power gamma PV raised to power gamma is equal to P2 V2 raised to power gamma. We know that the initial pressure here was 16 atm into volume, which was given to be 1 raised to power 1.5, is equals to pressure at B, what we have to find out, and the volume is given to be 4 over here. So we can say that pressure B is nothing but 16 upon 4 raised to power 3 by 2, right, which is nothing but 16 upon 8, that is 2 atms. So the pressure at B is 2 atm. Now we have to find the pressure at C. Now this is governed by isothermal process. Okay. Now we can say that the pressure has remained constant. Yeah, you knew that because this is the isobaric process. That means the pressure at B is same as pressure at C. So you can directly write it as pressure B equals 2 atm. So at both the positions the pressure are equal to be 2 atm. Now let's try to answer the third question, which is what is the temperature at B and temperature at C. Now one thing you can do is you have the pressure at B as you had computed in the previous question. You have the volume at B, you can find the temperature at B, which is nothing but governed by the ideal gas equation. PV VB is equal to NR TB. Right. Now the moles of the gas you don't know, first of all, right, that you need to find. Or at the second state you have P2V PCVC equals NR TC. So this is the scenario at two positions, right? So we have either you could do is find the value of NR somehow, or the other thing you could do is for both these NR is a constant. So basically you just divide this equation, PBVB upon TB is equals to PCVC upon TC, right? Now we know that PB and PC are equal, so we have VB upon TB equals to VC upon TC, right? Okay. Now we can find the volume basically for C. The temperature for B could be directly found as well. As it is an adiabatic process, we have the equation relating temperature and volume, which is TA VA raised to power gamma minus 1 equals to TB VB raised to power gamma minus 1. So the temperature at A was given to us as 600 kelvins. So 600 into volume, which was 1 at there, 0.5 equals to temperature at B, which we have to find out, and 4 raised to power 0.5. So which gives us TB as 300 Kelvin. Right. So we can now plug in over here this value. So we get a relation between the two properties. Okay. So what we have is VB upon TB, which is nothing but 4 upon TB is 300 kelvins equals to volume at C upon temperature at C. Now we know that AC was a isothermal process. A to C was isothermal. So the temperature at A is same as temperature at C, which is equals to 600 kelvins. So the part has already been done, but I was calculating this in order to relate the volumes as well, right? So we can say that temperature at C was 4 upon 300 is equal to VC upon 600. So this is 2. We get directly VC is equal to 8 liters. Alright. Now let's try to review this question. What we had was an ideal gas equation, which is taken an ideal gas at 600 degrees Kelvin at 16 atm and 1 liter volume. It is taken through two processes. One is adiabatic and one is isothermal. So by just looking at the graph, we were able to find out which is adiabatic because it had a higher slope. Okay. Next thing we were required to find is the pressure at both the locations. One thing we could infer just by looking at the graph is that the process from B to C was an isobaric process. So the pressure at both the locations B and C would be same. So we just use the equation for the constraint equation relating P and V in the adiabatic process to find the pressure at B is equals to 2 atm, and the pressure at C was also 2 atm therefore. Now we have to find the temperature at both the locations B and C. Now we know that C is A to C was an isothermal process. So the temperature would have already remained same. So temperature of C was directly 2 atm. Temperature of B could be related directly by using the constraint equation relating temperature and volume of adiabatic equation, which is T1 V1 raised to power gamma minus 1 is equal to T2 V2 raised to power gamma minus 1. Using that, we found the temperature at B. Now we could relate the volume of the both positions as well. Okay, so this was one type of question based on the PV curve, right? So the essence of the PV diagram questions is that you have to figure out which type of processes we are dealing with just by looking and infer as much information as possible by looking at the questions at the graph, right? So another question we have is in which 6 gram of hydrogen gas, there are two processes taking place. Now this diagram has not been drawn properly. Let's draw it again. The gas is ideally taken through two processes. One is an isothermal process and one is isochoric process, right? The first process is isothermal, it is given to you, and this is isochoric process from position 1 to 2 to 3, right? So basically you have 6 gram of hydrogen gas at a temperature of 273 Kelvin, and it is isothermally expanded to 5 times its volume. 5 times its initial volume. Okay. Then isochorically, heated such that pressure final is equal to the initial state. You have to find is delta Q for the whole process, that is from 1 to 3, right? This you have to find out. So let's try and first of all understand what we are dealing with. Okay, so the gas grows from A to B, 1 to 2, then 2 to 3, and the initial volume here was, let's suppose, V1. So the final volume at 2 is 5 V1, that is given to us, and we know that these two are at same position, that the pressure at first initial state, that is 1, and the final state is same. So now you have to find out the total heat input or heat taken in the whole process. So one thing is for sure, this 1 to 3 could be split into two parts, that is the heat intake from in the process 1 to 2, and the heat intake from in the process 2 to 3, right? So if you are able to find these individually, we can directly calculate the value for the whole process, right? So let's try and calculate Q12. Q12 would be nothing but delta U, change in internal energy for the process, plus the work for the process, right? Now we know that 1,2 is a isothermal process. So we know that delta U would be 0, right? And the work would be given by 2.303 nRT log of V2 upon V1, right? Which is nothing but 2.303 moles are basically 6 gram of oxygen. So 1 mole of hydrogen is 2 grams weight. So there are 3 moles, right? Into 8.3 into temperature, which is given as 273 Kelvin, into log of 5 V1, as the volume has expanded to 5 times, okay, upon V1. So which gives us the value as work done for 1 to 2 is given to be 10942.4 joules, right? And the delta Q would also be equal to work 1 to 2, which is equal to 194.2, sorry, 10,942.4 joules. Now, we have to find out the second part. Second part is delta Q 2 to 3, which is nothing but delta U 2 to 3 plus work 2 to 3. Now we know that 2 to 3 is a isochoric process. Now we have that delta V is 0. We know that, therefore work would also be 0. So we can say that delta Q 2 to 3 is equals to delta U 2 to 3. Basically, we have to find is delta U, which is given by nr delta T upon gamma minus 1, right? And which could be very easily be calculated, right? And hydrogen gas is basically H2, therefore it's a triatomic molecule. We have gamma is equal to 7 by 5. So moles are given to be 6 by 2, that is 3 moles into 8.303. Now we have to find the delta T. T we have to find out. So delta T upon 2 by 5. So this is our equation. We have to find the value for delta T. Delta T is basically temperature of 3 minus temperature of 2. Now as we are going through a isochoric process, we can make use of the constraint equation, which says that PV is equal to isochoric. For isochoric, we have P1 T1 equals to P2 T2. So here we can say that P2 T2 is equals to P3 T3, right? And to find the temperature at the second position is quite straightforward, right? Why? Because T1 was equals to T2. This was because 1, 2 was isothermal. So at the second point, the temperature would be same, which is nothing but the value as 273 kelvins. For 1, 2, the pressure had remained constant. The temperature had remained constant. So for this process, P1 V1 was equals to P2 V2. Now we know that the pressure initially was given to us as some, we are not given actually. So we can make the use of this property as the volume has expanded to 5 times. So we can just say that P1 V1 equals to P2 into 5 V1. So we can say that V1 V1 gets cancelled out. P2 is nothing but P1 by 5, right? So what we had was P2 upon T2 is equals to P3 upon T3, which is the isochoric process. So P1 upon 5 upon T2, which is nothing but T1, equals P3, which is nothing but P1 upon T3. So P1 P1 cancels out. T3 is nothing but 5 times T1. So that is 5 times 273 kelvins. Now we can plug in this value for delta T, right? So this was 3 times. So the work done for 1 to 2, so for 2 to 3 was 6 by 2 into R into delta T, that is 4 times 273 upon 2 into 5, which gives us the value for delta W 2 to 3, delta U, this was delta U, my mistake. So this was delta U from 2 to 3 is given to be 67977 joules. If you calculate this, you will get this. So this was basically equals to delta Q. for 2 to 3 process, because isochoric does not have a work contribution in the energy. So we get the value for delta Q for 2 to 3 as 6799977 joules. So now we can find the total energy input from 1 to 3, which is nothing but the summation of both the processes heat input. So on adding them, what we get is 10942.4 plus 67977, that is equals to 78,919.4 joules. So in this question also, we just first of all understood what are the processes doing, right? The first process was isothermal process. The second process was isochoric process. So using that and the governing equations, we found the various states. First of all, we had to find the total energy input. So we basically split the energy intake into 2 parts, undergoing the first process and undergoing the second process. And we tried to find out both these values separately and then added them. Okay. So let's do one last question on PV curves, which is this. The PV diagram is given to be this type. Okay. There are humps like this in the curve. The gas is taken from state 1 to 2 and then 2 to 3. Okay. The volume at all these states is V1, V2 and V3. Right. What does the question says is, 1 mole of a perfect gas or an ideal gas initial pressure is equal to 10 raised to power 5 Newton per meter square and temperature is equal to 300 Kelvin respectively, expands isothermally. Okay. Till volume doubles. Then adiabatically till volume again doubles. Right. Find the final temperature and pressure of the gas. Also find the work done for isothermal and the adiabatic process. Right. So what we are given is, this was V1, let's suppose. This process is given to us as isothermal. And this led to the volume being doubled. Right. And this is given to us as adiabatic process. And the volume still doubled. That means it went to 4V1. Right. At 1 the state is, pressure is given to us, the temperature is given to us, and the moles are given to us. So we can find the volume first of all at the first scenario, which is P1 or nRT1 upon P1, which is nothing but 1 mole of a gas multiplied by 8.3 into temperature, which is given to us 300 kelvins upon pressure, which is 10 raised to power 5, which gives us the value of volume 1 as 10 raised to power 3, this is 24.9 into 10 raised to power minus 3, which is nothing but 0.0249 meter cube. Right. Now what we are required to find is the work for the isothermal process, work for the adiabatic process, the final temperature as well as final pressure. So let's try to find the states at second point. So V2 has just doubled V1, that we know, as T1 is equals to T2. This you can say that because 1 to 2 is isothermal. Right. Now one thing is for sure, P1 V1 equals to P2 V2, right? So if P1 V1 equals to P2 into V2, which is 2 V1, so we can say that pressure 2 is pressure 1 upon 2, which is nothing but 10 raised to power 5 upon 2 Newton per meter square. Now we have reached the second state, right? Now let's try to find out the parameters at the third state. So one thing we can say is the 2 to 3 is a adiabatic process. So adiabatic process has the property that PV raised to power gamma, P1 V1 raised to power gamma is equal to P2 V2 raised to power gamma, right? And the volume has still doubled. So we can say that P2 V2 raised to power gamma equals to P3 into 2 V2 raised to power gamma, right? So P3 is given to be P2 into 1 by 2 raised to power gamma. Now the important thing over here is the gamma to us is given as 1.4. So making the use of it, the pressure at 2 was 10 raised to power 5 upon 2 into half of 1.4, which gives us the pressure at the third location as 1.9 into 10 raised to power 4 Newton per meter square. So this is the final pressure at that location. We are also required to find the temperature at the final location. So we can write the equation relating temperature and volume. So T2 V2 raised to power gamma minus 1 equals to T3 V3 raised to power gamma minus 1. So T2 is nothing but the same temperature as the initial, that was 300. So V2 upon V3 raised to power gamma minus 1 equals to T3, which is nothing but 300 as the volume has doubled raised to power 0.4, which gives us the temperature as 227.35 Kelvin. So this is the final temperature. Now let's try to find the work done. Work done for the whole process, that is 1 to 3, is given by, we will not write delta actually, we will write work 1 to 2 plus work 2 to 3. Work 1 to 2 is for a isothermal process. So 2.303 into nRT log of V2 upon V1 plus 2 to 3 is the adiabatic process, which is nothing but minus of the change in internal energy, that is nR T2 minus of T3 upon gamma minus 1. So using these equations, we can say that this would be nothing but nR we can take common out, which gives us 2.303, the initial temperature which was 300 into log of 2 plus T2 minus T3, which is nothing but 300 minus 227.35 upon 0.4. So if n is given to us as 1, R is given to 8.3. So using these values, we can find the total work to be done as 3233.56 joules. So basically in this question also, so overall the basic essence of solving the PV diagram questions is you have to first figure out which type of processes you are dealing with and try to extract as much information by just knowing what process you are dealing with and the given constraints in the question. By looking at the graph, you can identify which parameter is remaining constant, and by using the constraint equations for all these processes, you can find a lot of information that is useful and comes handy in solving the questions. So that's all for today. Thank you.